All right, last example. So we want to work out this particular line integral where you're given the vector field f. Notice it's a three-dimensional vector field. Whoops, 1, 2, 3 components. And then you're given the parameterization of your curve. That's nice, isn't it? You don't have to try to parameterize yourself. It's actually given to you. And we want to work out this line integral. Couple of comments. Hopefully you recognize this space curve. So this is the space curve. You don't have to draw it, but I will. Let's see, when we plug in 0, we are at 1 on the x-axis and 0 everywhere else. And this thing is spiraling around the z-axis. I don't know exactly where we end up. Let's see, at 2 pi, we're going to be back at 1, 0, and 2 pi. So I think we're going to be back up here. I probably have too many spirals in there, but it doesn't really matter. That's more or less what it looks like. So our curve is not closed. If it was, we could hope that this thing was conservative and then just write down 0, but it's not closed, so the answer may not be 0. It still could be. Now we want to figure out whether or not this function f is conservative or not. Unfortunately, we can't use our little test, is p partial y equal to q partial x. That doesn't apply here because there's this third component. So to be able to figure out whether or not f is conservative, we're going to have to look for a potential function. So before we do that, before we try to use any theory, I thought it would be good for us to remind ourselves how you would do this with the direct approach, the standard approach here. So let's do that first, and then we'll come back and we'll figure out whether or not this function f is conservative and see if we can use it. So if I wanted to do it directly, I know that the integral over c of f dot dr equals, I'm going to need all the space I can get, the integral from 0 to 2 pi. Then you take your parameterization, x is cosine t, y is sine t, z is t. You plug that into your f. So I'm going to have the vector 2 cosine t times t. So let's actually simplify that and write that as 2t cosine t plus the sine of t. Oh my. Comma, let's see, cosine of t times cosine of the sine of t, oh yes, comma, and then the last one is just x squared, so cosine squared of t. Who came up with this problem? Now we're going to dot with r prime, which is minus sine of t, cosine of t 1, and oh boy, I need a little bit more room. Can we squeeze a dt in there? Yes, there we go. Wowee. So if I wanted to, I could compute the dot product. I really don't feel the need to. But you're going to get something very, very horrible. And it's not just going to be horrible in the sense of a little by parts with a t and a cosine t. It's not just going to be horrible in the sense of products of sines and cosines. There's actually sines of sines and cosines of sines, and this is just going to be a nightmare. So at this point, if you did try this directly, if you forgot about all the theory and you try this directly, I really want you to recognize that's a really horrible problem. Dr. Klein likes to challenge us, but this even seems a bit much for him to assign. I wonder if there's another way that I could do this. And a lot of times there is a better way than just doing it directly, especially when it seems this nasty, at least for the kinds of problems that we're going to be looking at. So let's go back now and ask ourselves, can we do this directly? We should leave a little note here so that you know what happened. Let's just say, yuck. I think that communicates the situation quite well. So now, back to the theory. Can we figure out whether or not this function is conservative? And again, we don't have a little test. We're going to have to just do it directly. I think to save time on the video, I'm going to go ahead and tell you the answer. So I'd like you to pause the video, see if you can figure it out. And you're going to do that by actually looking for a potential function. So if you're able to find the potential function, you know it's conservative. Otherwise, it probably isn't. So pause the video, work that out yourself. And now, let me tell you, big F is conservative. And it has potential function little f of x, y, z equals x squared z plus x sine y. You could throw in a constant if you want. I'll just leave my constant equal to 0. And so the point is, the integral that I want, this integral, is equal to f of r of 2 pi minus f of r of 0. Well, r of 2 pi, remember r was cosine t, sine t 0, so this is going to be f of cosine of 2 pi is 1, sine of 2 pi is 0, and then t is just 2 pi, so that's in the z component, minus f of r of 0 is 1, 0, 0. And now I'm going to look at my little function. So f of 1, 0 pi, I'm plugging 1, 0, 2 pi into my f, 1 for x, 0 for y, 2 pi for z, and I just get 2 pi. And I'm going to subtract, and I plug in 1, 0, 0, and oh, look, I just get out 0. So this is just 2 pi. So it turns out that this nasty integral, which would be very hard to compute directly, you actually know the answer to. It's just 2 pi. So I'll end this video here. That's 13.3. We're done with that one. In the next lecture, in 13.4, we're going to learn another tool to make evaluating line integrals a little bit easier, and that tool is called Green's theorem. So I'm excited to show that to you. We'll get to that one next week.